All right, part 3 here. Then we're going to talk about driven oscillations. Okay, so this is when you 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 push down a spring. All right, it's going to go, but then you're also pushing below it. Okay, sort of like that. Now, you know that if you're not driving it, if you're not forcing it to keep going, boom, 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 it's going to oscillate on its own with a particular frequency. Okay, and let's call that frequency omega. I'm gonna call it omega prime. Okay, and it's basically the square root of k over m. Okay, now if we want to take into account damping, then we've got to be a little careful, and omega prime is actually going to become square root of k over m minus b over 2m, quantity squared. Okay, so the damping has a small effect on the frequency we talked about with free oscillations. Okay, so we might think of that as omega 0 right there. Actually, that would be omega 0 squared, wouldn't it? Okay, so this is approximately omega 0. Okay, that sort of thing there. Okay, now, so we have this natural frequency at which the object wants to oscillate. And if we force it to oscillate, okay, and what we have here is the results of some experiment where they're forcing an oscillation and they're controlling the amount of damping in the situation. All right, but what we are going to see is that there's a peak in the motion, okay, and that peak occurs around this natural frequency for the thing. Okay, and so what that basically means is if the thing wants to oscillate like this, okay, I got to do it in slow motion for the camera here. All right, and I'm pushing at some low frequency. This is super hard. Okay, I'm not going to get very much response out of my spring mass. Okay, I'm not going to get too much response there. Okay, and so I might be pushing it down here in this region, and I'm not going to get very much response out of it. Okay, so on the other hand, okay, if it's trying to move like this, and I'm like, moving it like crazy, okay, I'm going to have the same problem. I may be forcing it around up here, but I'm not going to get much response out of it. However, if it's moving like that and I start to push it like that, okay, then it's going to go crazy. I'm going to get a lot of response. And the exact amount of response will depend on how much damping I have. Okay. If there's a lot of damping in the system, which could come from friction or air resistance, then I'm going to get a curve like that red one there. So it's just got a little modest peak there. Okay. However, if I had a system that doesn't have very much damping at all, then I'm going to get a very large response like this. Okay. Now, one way to tell if you've got a lot of damping or not in a lot of systems is just to see how long they're going to oscillate for. So like a bell, bing, a bell you might ring, or a guitar string that you pluck. It's very little damping in that system, and so it's going to go for a very long time. The flip side of that is if we try to drive those things, we can get a lot of response out of it for just a little tiny effort. Okay, just a little tiny effort. Okay, now an important idea here is the idea of a Q value. Okay, now the Q value has to do with how peaked this thing is. So let me get rid of some of these marks over here if I can. Hello. Try again. It's getting a little messy. Okay. So the Q value has to do with how peaked those things are. So my red here, and there's a certain height and it has a certain width. And the Q value has to do with that height to width ratio. All right. And so if we have something else like the sort of golden yellow color or orange color there, it's much taller at the same width. Okay. So sometimes it's called the height to half width ratio, that kind of thing like that. But the lower my gamma value, because I have less resistance, okay, the higher that peak becomes, and this thing becomes really, really, really peaked. Okay. And so if you had a bell and you're trying to ring a bell, what you would find out very quickly is with your bell, you wouldn't get much of anything at all until you got to the resonance frequency, and then you get crazy response, just like that. Okay. Now, a good example of that is, problems. Okay, that's okay. Is this. Okay, so I left a link to this video. Okay, have you ever seen these videos where people sing and they break a glass? Oh, pop that thing right up. So it talks about what's going on with that. It's really cool. It's a really fun video and talks about some of these issues and talks about sort of specifically what causes the wine glass to break. What's the physics behind how all that happens? And it has to do with these driven oscillations and the fact that a wine glass, like, if you thump it, ding, it'll ring for ding, a second or two. And that means it's a very high Q system. Okay, so it'd be very peaked, and because there's very little damping in it. Okay, so that means just the energy of your voice alone could break it. Okay. Anyway, I think that's all I'll talk about on that one there. Because I want to talk a little bit about the Tacoma Narrow Bridge, because one of the questions that, is not addressed most of the time when people talk about the Tacoma Narrow Bridge is exactly what are the mechanisms that led to its collapse. All right, people will say, oh, it went into a resonance mode and busted. Yes, absolutely that's what happened. But why? Why did it go into a resonance mode? Specifically, why did wind cause it to do that? I mean, after all, the bridge is here. Okay, let's say the bridge is here. The wind's blowing like this. So how is it possible that the bridge ended up moving up and down because the wind was going this way, right? I mean, it's not like the wind was going, okay, that would be easy to understand. But the wind is blowing across like this. So what the heck is going on? Well, the answer is in the fact that in real objects, there is never just one mode of oscillation, okay? There's never just one mode of oscillation, all right? And we'll talk more about this when we get to a topic called standing waves. But for now, just realize that things can wiggle in different directions, all right? So you've got the bridge, and it can clearly wiggle up and down like this. However, it can also wiggle like this. And what is a little bit strange, but this is the answer, is that this motion here can cause this motion here. It actually works the other way around too. If you had wind underneath it and you went, pff, 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 it would start to do this as well. Okay, so it's kind of strange. But those are called coupled oscillations. The two modes, going like this and going like this, they're not independent of each other. They're connected together because they're both part of the bridge. Okay. So let's look closely. Okay, take a look at this over here, side of the bridge. Okay, now if I was to draw, I'm going to do it here in a second, looking at sort of a cross section of the bridge, all right, we would get something like this. Okay. All right. So here's the road deck right here. And then there are these supports here and here. And then there'd be like some bracing underneath it, different sorts, that kind of thing there. Okay. Now, traditionally what had been done up to that point is, instead of, can you kind of see that it's like a flat panel? It's like a wall in there. Traditionally up to that point, what they did was they put in like beams. So it was like a truss. All right. Just like that. Now, putting together a truss is pretty expensive because it takes much longer. If you've got a big panel that you can just use rivets and bolt that sucker into place, that's quick. All right, that's super quick. It means the people working on it can do it very rapidly, and so it doesn't take as much time. You don't have to pay them as much. Okay, so it's much less expensive. And so the designers of this bridge thought, well, let's do it with panels because it's going to be cheaper, and we think it'll work just as well. So they didn't put in open trusses. Okay, so whoa. That turned out to be the thing that doomed it from the start. Okay, because let me try and draw another picture over here. Okay, so here's my truss. Or not my truss, but here's my cross section of my bridge. All right. So if the wind comes along in a slightly different color here, the wind comes along, it's blowing from this direction. Okay. The wind is going to hit it, and it's going to be just maybe slightly coming down as it travels, and other times it'll be slightly going up as it travels. Anyway, what's going to happen is on the back side of this bridge, from the wind, that wind is going to come across. It's going to move like this, which is going to kind of create a low pressure area here and a high pressure area here, which is going to help to lift it. Okay, so it's going to kind of suck it up just a tiny bit, but not too much. But this thing's going to come off of here, and it's going to peel, and there's going to be a vortex. Okay, so if you've ever seen a stream or something like that, you put a stick, you put your hand in the stream, you see that vortex behind it. Okay, now that vortex is going to cause the bridge to tilt. All right, and so it's going to end up doing this. Okay, now if it does that a little too much, then the wind ends up moving this way and putting the vortex on the bottom. Okay, that ends up tilting the bridge back this way. Okay, and now we're going to get the vortex back on this side. Okay, so as this thing twists differently, the vortex on the back side of that thing keeps flip-flopping. Okay, and so it starts to do this sort of thing here. Okay, and then that ends up being connected to this kind of motion. All right, and so really this was the driver created by the wind. All right, and that ended up causing it to do this sort of thing here. Okay, and so the cool movie that you got to see part of. All right, and there's a longer version if you want to go hunt for it. Just search on Tacoma Narrows Bridge, and you can find the long version of it. They talk a little bit more about it, but the University of Washington in Washington State is fairly close by, and they called some engineers and said, "Hey, come, we got this problem," because it had a history of going up and down almost from day one, and it didn't last for very long, just a few weeks, I believe, if that. And so they called it Galloping Gertie. And people would drive over the bridge while it was going up and down because it was like a carnival ride. They're like, woohoo! Okay, going across this thing in their cars. Anyway, so our grandparents were a lot braver about entertainment than we usually are. Anyway, so, people worried about it because sometimes it really moved a lot. And sometimes they would shut it down because it was moving so much that it was dangerous for cars to drive on. They couldn't keep going straight. So anyway, this guy comes out, and he's an engineer, and he's like, okay, well, let's take some video. He didn't have videos, but let's take some films, make some movies here, and make some measurements and blah, blah, blah. And while he just happened to be filming it when it collapsed. Okay. So it almost seems like it was planned, but it wasn't. Okay. He just happened to be there when it collapsed. All right. And then he and his team were the people that figured out that these using these panels instead of having an open structure is what actually created the problem. Okay. And there weren't very many bridges that were built with the closed panels, and they quit doing that right away. And bridge engineers like, that's not good for business if your bridge keeps collapsing. All right. Anyway, there we go. So I'm going to do one more video for you. I'll do some numbers with an example for you. Okay.